Let me get this slide going here, and I don't think so. Appreciate it. Do you have a, let's see, I'm looking for my slides. Is this hooked up to the internet?
Yes, I did it last night. Just make sure.
Oh, for the CEUs? Okay. It doesn't matter. I mean, tapping the tile at it is better probably, but not the end of the world. Did you pass out the 2020 changes handout already? What about the homework stuff? That's it right there, right? So the new one that I gave you
I
is,
gave it to them.
oh no, that was the one of the ones you gave out.
I did.
Great. No, it's fine. I'm just gonna use those for, throughout the day, so it's fine with
But,
that.
by the way, I need the answers for the,
Okay, all right.
so I can put it on the, is it ready? I gave them access to the call, so
All right.
it's gonna be my email.
I have them started, so they're in my, in that bucket of papers, probably toward the, no, they're in, hold on, let me see, hold on a second, I might have it. I know I've gotten started doing that in nope, I lied. Probably in that, bucket with the files. They're probably in that bucket with the files. So, check the very top of that bucket with all the files and see if there's in there. There's like 2 pages that are loose that haven't started. Yeah.
Just let me know.
I'll take my purse. All right.
See you guys later.
Well, since I don't have an answer key for that answer or that little pretest handy, let's go through that really quickly and see if there's anything I can answer for you. If you guys already filled out your answer key for that, for the pretest, I should give y'all an answer key.
Mm-hmm.
Can y'all pass that forward to me, or just pass them over to your left, I guess, and then I'll come grab them at the end of the row there.
Even if we're not done, right?
Yeah, just whatever your answers that you've got right now. I mean, you keep the test, right? But just give me the answer key just to give me an idea.
Set them here?
Hmm? Yeah, I'll come back and grab them. Huh. Shouldn't have broken that. No, you could break those. Everybody have these phone numbers written down. This is my cell phone number here. This is Mel's cell phone number. If you don't have those jotted down, you should have my cell phone on the back side or the front side of this card right here. So on your name tag, so you've got that. Just save that in your phone. You never know when you might need it. I'll take text messages throughout the week. And so just to kind of just warm up and kind of introduce myself and then kind of get rolling. My name's Mitchell Talbert. I've been in electrical trade since March the 9th of 1987. And you might think that's weird that I would know the exact date that I started in the electrical trade. And I know that date though because it was the U.S. Army is where I started. So I got my first taste of the electrical world in the military. And I was an exterior lineman, actually a pole jock for the first few years. And then I got out in the civilian trade in 1994. And I mean, I've been pretty much every role that you can imagine in the commercial electrical world. I've done residential on a real limited basis, and I hated every bit of it that I've done. So every time I do a residential job, I remind myself why it is that I don't want to do residential, right? But at any rate, been mostly commercial, but ditch digger, floor sweeper, skyhook fetcher, you name it. I've probably done every bit of that. I've not done very much industrial stuff. I've done some, but it's been pretty limited. Some of your hazardous locations and stuff. I've got some working knowledge of it, but I'm not an expert by any means. But been a project manager, been a contractor, and currently I work as the manager of the plan review department for the city of Austin. So I've got a group of folks that work under me that are subject matter experts in either the IBC, which is the International Building Code, or I've got several electrical reviewers, I've got plumbing reviewers, mechanical reviewers. And it is true what they say about plumbers. They're always full of drama. It's always something every day. You know what they call a plumber with an IQ of 78, don't you? Boss. Sorry. I tested the water to make sure I didn't have a bunch of plumbers. I figured just one is not going to be too bad. I could probably get away with that joke. But at any rate, so I look at plans pretty much all week long, and it's broadened my horizon because I spent so much time in this code book that I felt like I knew it pretty well. But then I get into some of the other code books like the IBC. I don't know if you guys ever had any familiarity with building code, but it makes this thing look like chump change. I'm telling you, you think ours flips you around. I mean, sometimes in this book, you'll be looking for something that'll tell you to go somewhere else, right? And that's not too bad. It's the stuff in here that doesn't tell you that, oh yeah, by the way, don't forget the other parts that are included with this, right? Sometimes they talk about one part in one chapter, and then there's another part that is absolutely integral to that step or that process, but they don't even talk about it at all or mention it. And of course, it's further in the back of the book. For example, like when we're talking about wiring capacity, right? You guys know that you put a certain number of wires in a conduit. You can physically fit a certain number of wires in a conduit, like in a 1 inch. How many number 12s can you put in a 1 inch?
27.
27? It's a lot, right? But then when you go to doing your ampacity, when you start mixing a bunch of wires that carry current inside a pipe, they create heat. And so you have to derate because of that heat, right? So effectively, there's a limit to the number of those that you can put in there that's a lot smaller than 27. So those two pieces are so related to each other, you can't ignore one for the other. In other words, you can put 27 of them in there.
Physically, okay.
It'll fit physically, but thermally, when you come to derating it, when you do that, you're going to end up with half the ampacity that you probably had before, right? And so those are things that in our code book, it doesn't really mention it. If you didn't know those are related or linked together or have any way of making sure you remember those two pieces, then it's really easy to forget the other half of it, right? And that's kind of the problem with this test is, sometimes they'll give you half of the problem, but you can't forget the other half that matters, and they won't say anything about that. So knowing that part of it and making sure that you include the stuff that you have to for the calculations is probably the toughest thing for master's test. There's always the fact that, on a test question, they never ask a question straight up. I don't know why that is, but they can't just ask you for the ampacity of 12 number 12s in a conduit. But they always kind of ask you, if you got one of them that does this and one of them does that and 10 more that do this, what's the ampacity of one of them? And it's like, well, at the end of the day, that's 12 wires and in a conduit. What's the ampacity of it really? It boils down to it. So I've got a couple of master's licenses. Throughout the years, I've gone through and worked for a couple of different companies. And when I started working for a utility contractor here in Dallas, or Fort Worth actually, they just hired me to just be their master of record, and I flew around the country for about 8 months, and I'm now licensed in 25 U.S. states, and I've also got a couple of utility contractors licenses. I've got some boring and tunneling licenses in South Carolina. I'm a certified electrical inspector, residential and commercial, and plans examiner, and so on and so forth. So I've had my fair share of exams, I guess, is my bottom line. And the only reason why I think it's important to tell you all that is because I really have sit in front of that computer screen and struggle with the same questions that you guys are facing now. And it gives me a little bit of a better perspective than somebody that maybe wouldn't have, right? And so I'll try to keep everything that we talk about in the next 2 days as relevant as I can. Sometimes you may not realize why we're talking about a certain subject, but it's because it's an underpinning part of a lot of questions, right? It's a core concept that you have to understand to be able to know, for example, that if I put more than 9 wires in a conduit, then I have to start taking a 50% derating. Did y'all already know that? Most of y'all do that, right?
Yeah.
He said I could put 27 of them in a pipe. But if 29 of those carry current, that's the limit. If I hit a 10th one, it's a 50% derating of the ampacity of that conductor.
I have a question for you on ampacity and derating. In the code book, and I can't sit here and recite
Say it verbatim.
all the code sections and everything, but it says that if you have a current carrying conductor and a dedicated neutral, it is called one current carrying conductor. If you have a full boat where you've got A, B, and C phase and a common neutral, it is considered 4 current carrying conductors. But if you're dealing with Romex, a hot and a neutral, it's considered 2 current carrying conductors.
So you stepped in a big pile of knowledge right there, right? First of all, the word neutral, you know what, I think it's a good question, but I think it's a little premature just yet.
Okay.
If I start, but you're on the right track. You're talking about 310.15 B5, I think, isn't it? Is where your answer is. But I don't, it's a good question. I don't want to ignore it, but I'm going to do wire ampacity here in a minute, and I think that's going to probably kind of be part of that. Page.
My main question was why in Romex the neutral is considered current carrying
Because
when
those
it's
are
only
gonna-
2 circuits or 2 wire.
So the neutral's not really this is not a neutral, this is a grounded conductor, right?
Right.
Kind of like a pipeline. When you got, when you've got wire, in the circuit, or when you're running a circuit, let's say we've got find a good marker here. So when I've got, let's say we have a 120 volt circuit that's running off of a 20 amp breaker out to a receptacle, right? Actually, that's the way they've got that drawn backwards to the neutral or the grounded conductors on that side. But just for sake of purposes, it's kind of like a water pipe. You can't electricity won't flow unless it's got a loop, right? It's got to go out there and then come back. Well, if you've got 2 wires, then it's just like it's just like you're going to the grocery store. You got to go there, and the same car that you took to get there is going to go back the other side, right? So that white wire that's right here, if I have a black wire that's got 15 amps worth of line current, I've got 15 amps worth of load current coming back. I mean, it's just what it is. If y'all don't think that white wire carries current, take it loose one day and turn on. Just hold on to it. I promise you. Yeah. You can touch it in the panel as long as you got a good ground, right, and not get shocked. But you take it loose, you're going to be the ground, and you're going to see exactly what I mean by that. It's a full current carrying conductor. It carries the same amount of current as that black wire does. In a case like that, that means they're appropriately going to give about the same amount of heat. So we have to count that. Now, if we carry another wire, though, and with Romex, with a 240 volt system, this works out real well. If I split the tab over here on this receptacle and I bring a separate hot over here, right? Then what happens is because the sine waves are nice and clean and we call them linear, when they meet on this neutral, it's kind of like this. If you look at it at a snapshot in time, right? When you've got current flow in this direction, you've got current flow in the other direction exactly at the same moment. So what happens is when they meet here in the middle, excuse me, I got this drawn backwards, they actually meet at opposite directions on that neutral conductor, and they cancel each other out except for the difference between the two. So if I had one here and one there, I'm just carrying the difference between those two. So if this is 15 amps and this is 5 amps, for example, then I'm only carrying the net difference on that white wire. And so we don't count it. Even though it could carry quite a bit of current, it doesn't carry the same amount of current that the other two do. So 12.2 then, we don't count this neutral because it's not really a full current carrying conductor.
Right, but
And
the way the code book reads, if you have a dedicated neutral, you don't have to count it as current carrying.
No,
but
you
if
do.
you have a boat,
You do, because here's the thing, the word dedicated neutral is not really a term. what that is, when you talk about a dedicated neutral, you're talking about a grounded conductor. And grounded conductors are always gonna count if they are the only wire, because they have to count. I mean, they literally are the pipeline that carries the full, they're the same as the line conductor, right?
Why would you have to derate the wires in a Romex cable?
It's not that you have to derate the wire and Romex cable, it's when you stack them and bundle them together.
Okay,
And run them
then you would
for,
have
you know,
to
for running for.
derate. Okay.
Either if you go through a header that's got some kind of fire barrier in it, that makes you start calculating them if you stack them in the same opening.
Okay.
Or it said 24 inches or longer.
Or 24 inches or longer, yeah. So if you look at your code book to kind of get based on, if you look on page 160, they moved it around a little bit, and it's under 31015 E now. It's on the left-hand side of page 160. It is 31015 E. Over on the left-hand side, kind of in the middle of the left-hand column, page 160, where it says E, neutral conductor. So first and foremost, you have to define the term neutral before we really get into that, because if we talk about this as a dedicated neutral, it gets kind of confusing. Truth is that a grounded conductor, the term grounded, it sounds like we're talking about a green wire, but we're not, right? A green wire or bare wire would be a grounding conductor, and that's different than a grounded conductor, right? Grounded conductor is an intentionally grounded conductor, and if you think about this drawing here, this wire right here is grounded at that panel. It is, because we tie that neutral bar to your grounding electrodes system. So at the service point, that is, and we intentionally intend for that thing to carry current during normal operating procedures. Yep.
So it says it carries the unbalanced current from the other conductors.
So once we don't, if I just have this wire right here, which is a black and a white, that white wire is not a neutral. It's a grounded conductor. And we call it a neutral all the time in the trade, right? I've called every white wire, gray wire I've ever seen in my entire life a neutral, but truth is it's not a neutral if it just has one other wire that it's dedicated to. If it has one wire that's dedicated to, then the term neutral means that I don't take sides, and if there's only one side, well, then that means I can't really say I'm neutral to anything. Of course, I'm fully along with whatever the one side that I have, and so that's why we call this a grounded conductor, to differentiate that from a neutral. So this wouldn't be a neutral, this would be a grounded conductor. Now this would be a neutral because it does share common pathways with all three, or in the case of a two-wire like this, the two-wire. So we call that a common carrier, a common conductor, or a neutral, right? So once I get that term labeled as a neutral, then this section here applies, and this tells me when I count it. But remember, we're talking about neutrals here. We're not talking about grounded conductors, because grounded conductors aren't on that list because we always count those. Does that make sense? So they're just, as a general rule.
So the top one would be 2, not 1.
So 12-2 Romex.
No, that top equation would be 2, not 1.
This one? Yeah, I'm sorry. You're right. I'm so sorry.
No, I'm just-
That's exactly right. Yeah, sorry. But a 12-3 Romex, right, means I've got a black, a red, and a white. That means I'm going to count this one, I'm going to count this one, but I'm not going to count this one because it really truly is a neutral. Now in a commercial setting, those are all, we're talking about linear loads, right? Linear loads are going to be things that just use electricity and put it right back. It just uses a portion of it, but it doesn't change the characteristic of the sine wave, right? So nonlinear loads would be things like electronic circuit boards, where they convert it to DC current. When they spit it back to the AC side, it's going to look completely different than the sine wave that started out as. So that modified wave then doesn't cancel out on the neutral like it would have before. So for example, if one of these is linear but the other one's got some jagged sections in it, the only reason why that cancellation happens is because they look exactly the same. So on a neutral conductor, for nonlinear loads like LED lighting, I don't know, have you guys ever done any LED lighting? Every LED light you ever put in is a non-linear type load because it is got a circuit board that it's a drive. They call them drivers, right? So those things are going to modify the sine wave, and every bit of that load current, even in a condition like this, instead of being a subtractive, it can sometimes be additive. So you can actually have more on the neutral than you might have on any one individual phase conductor because of that. Things like inductive loads too, like motor loads, are also nonlinear. But things like a heater, like a heat strip or something like that, that would be a linear load. So those are things that have now, I mean, most of your three-phase circuits that you have, it'd be kind of hard to not calculate that neutral. But if you look at number 3, I believe, number 3 is talking about that, I guess that nonlinear load type. So we don't count it. We always count it if it's dedicated. So if it's dedicated neutral, it always counts. If it's not a dedicated neutral and there's 2 conductors and they just carry the difference, like this example, then I don't count the neutral. If I have 3 wires like this, I'm going to count it. You're going to have some potential here on this neutral, but then the final part is going to be whether or not we hit 51% of nonlinear loads. So if the majority, more than the majority of our loads are LED lighting or motor loads or something like that, then I would have to count that neutral. Generally speaking, on a service, we don't count the neutral. I mean, because there's just, I mean, there'll be some nonlinear loads there, but they're not going to be, 50% or more. But if I were to run a lighting panel board and nothing in that panel board was just, there was nothing in there but lighting, I'd have to count that neutral. I mean, it'd be kind of hard to not. On the test, they're not going to really get to that level of detail. I have seen some questions about nonlinear loads, but they've been pretty rare. You will have some questions though where they ask you to derate it, but they'll flat out tell you if they're current conductors or not most of the time.
I mean, I've done a job before where they spec'd out super neutral
Sure. Okay.
as nonlinear loads.
Yeah. The triplins and the harmonics too are also, I mean, basically that's what's going on with the magnetic ballast and things like that. So it's not always just electronic stuff. Like in the case of a motor, which is an inductive load, it introduces harmonics, which is a form of a resistance or an impedance to a circuit, which means that you've got to take those factors into account. But they overheat the conductor more than they normally would. Really good question, right? I wasn't planning to dive that deep right off the bat, but hey, why not, right? If you really think about it, at the end of the day, what is the core thing that ties everything we do every day, day in, day out? What's the one core component that ties everything we do together? Wire. Well, wire nuts too, yeah. So I don't want to call myself a wire nut expert, but a wire. I mean, at the end of the day, everything that we do is focused around a conductor. If you think about it. I mean, really, everything else is just an ancillary thing that we run wire to make sure that and our job is to make sure that wire is sized properly for whatever it is we're connecting it to. That's really, at the end of the day, that's what we are. We're wiring, right? So understanding what these wires are and the labeling of them and kind of how they work together is really critical to not only your exam, but probably, understanding the core pieces of your trade. All right, well, let's see. So we were talking about this test deal here. Let's see if I can just, you guys really struggle on any one particular? Or are they all were all pretty much the same for you one way or the other?
Yeah, I gotta refresh on those parallel resistors. Yeah.
Parallel resistors,
Yeah.
they kind of suck. Series resistors are nice and easy, you just add them.
Yeah.
Right.
To answer that question, I'm really going to have to kind of give you a little bit more than just some cheap answers. So let me find my section here. We'll come back and catch this here in a second. You guys, you're familiar with Ohm's law, so you've probably seen the little pi wheel, and that pi wheel looks like this. You've probably seen it at some point in your career. There's a lot of math in there, though, and to be able to use that effectively, you got to remember the order of operations. Please excuse my dear Aunt Sally. Y'all remember that from algebra school? If you don't remember it, you're even worse off than you think. And to understand how to do a lot of these, you kind of have to remember in what order to do them. Like this square root sign up here, and then there's division operation. Which one do you do first, right? And it's important that you do them in the right order, or else your answer is going to be just nonsense, right? Now, luckily for you guys, there's only, on that entire chart, there's really only 2 formulas that matter. And those 2 formulas will answer every single Ohm's law question you'll ever run across, certainly in our trade. We don't really have resistors very often, but if we do have to know how to calculate them. So there's the P, the I, and sometimes you'll see that as an E, sometimes you'll see it as a V. And so there's the P, the V times I, and then the other one is the V, the I, and the R. What's I stand for?
Current.
Current. I thought that starts with a C. Right?
Amps.
For
Amps?
Yeah,
It stands for amps? I thought that started with an A.
induction.
No, induction would be kind of a form of
Yeah,
resistance,
that would
actually.
be,
Yeah.
I don't know, I would shoot.
Stands intensity of current.
Intensity.
I don't think anybody's ever referred to that in a long time. For me, I learned it just kind of like what I'm saying. I learned the PIE, which is, makes me always kind of hungry when I think about it. But, the I though doesn't really relate to anything to me directly. Like I have to stop and think about I, and in my mind go, okay, well, really what I'm talking about is A, because that's what we think about amps, right? Same thing with E. E stands for electromotive force, or commonly known as voltage, right? So a long time ago, somebody said, well, you know what? Instead of using PIE, you should use WAV. And I was like, no, that doesn't make any sense. They're like, you try it one day. Try it one day and see if you agree. It's also kind of easy to remember. That formula right there is probably the most common formula you'll use in the trade, period. Because we deal with watts all the time. I mean, a lot of your equipment comes in a nameplate rating that's in volt amps, which is the same thing as a watt. It's a unit of work or output of that equipment. And so whether we're talking about W being a VA, or whether we're talking about it as a W, or we're talking about it as a P, all of those are the same concept, right? It's the amount of work we get out of the two things at the bottom, which are the amps and the volts. And so this right here is a mathematical relationship of these three that kind of explains how they work with each other. This line always means to divide. In other words, if I'm looking for either one of these bottom numbers, I'm going to take the other bottom variable and I'm going to divide it into the top number to get whatever the missing piece is. So this is a division line. And this line down here is a multiplication line. Because I'm going to get the same amount of work. Let's say that A and V is Abe and Vic. There's two guys that work for me. I'm going to get the same amount of work per hour out of those guys if I have to whip them to death, right? Doesn't matter if Abe comes to work hungover from the night before, and so Victor's going to have to pick up the slack, right? It's exactly the way the relationship of these two work. Is these two are what we call inversely proportionately related. In other words, if one of them slacks off, the other one's got to pick up the slack, and they work just like that. If I go down by 50% production on this side, I got to go up 100% production on the other one, because I'm still going to get this number out of these two no matter what. Period. So the watt value is an involute number that just doesn't change. It is what the product of that work is. And if I move the voltage, for example, if this the V stands for volts, how many times have you put a meter on a receptacle and got exactly 120 volts? Show of hands. I mean exactly 120. Once or twice, probably, but it's been pretty rare, right? 115, 119, whatever, something around that difference. Back when I was a kid, it was 110 volts. Y'all remember that? So 110 and 220. You'll still hear people refer to it as 220, but it's not 220 anymore, it's 240. Well, sometimes now you're starting to see on equipment, you'll see 130 or 250. You know what I'm saying? Have y'all seen that before? So the equipment's rated 130 volts. Well, okay, this still remains the same. If that is rated for 5,000 watts, the reason why I'm telling you this is that as we've gotten better with our production equipment, and as we've gotten better with our manufacturing, as we've gotten better with the material types that we use, we've lowered the resistance of those values, which is another formula altogether. But what it's done is it's increased the voltage rating, so we've gradually over time had a higher voltage, and we'll probably see 130 volts as a common number here pretty soon before you know it, as we get to that point. But the bottom line is, if I change this up a little bit, what happens over here?
Goes down.
That's right, and it goes down in the same proportion. So let's say that's a 5% increase, which is probably not, but I'm just saying it just as a random number. If I have a 5% increase, then I have to have the same movement on this moving down by a factor of 5% or whatever it was to start with, right? They're inversely proportionately related. If it goes down 5%, you have to go up 10%. Yeah. So it's more than just 5%, but the bottom line is, if this goes up, that goes down, because I'm still going to get the same 5,000 watts. And this is an important concept to understand, because in the code book, we got a table that's really pretty common, and they use 115 volts on that table to give you an amperage for a motor, for example. So if I'm trying to get this number here, I got to remember that it's not always the same number right here, because that number right there is going to depend on what this number is right here. And so if I'm living out in the country and I'm at the end of a line, I might have 110 volts or 114 or something really small, because you have to lost enough voltage across that drop for the utility. And so that motor, if this number goes down, if the book tells me it's 10 amps at 115 volts, then I'm good if that's what I have at that house. But what if it is actually 120 volts that I'm calculating that at instead of 115? Well, then that's going to make this number go up. I'm sorry, down. Likewise, if I'm moving this number off this table at 115 volts, I got to remember that if I'm trying to get this number here and I take the 10 amps that's there on the table, to get this number, I would have gone this times this number here, which are the two table values. But I might have this number where I'm at, so I've got to make sure that I'm using this to get the right, I've got to make sure I'm using this to actually calculate. Then if I want to find out what the amps is later, I'd have to divide. I'm kind of going to confuse you. We're going to leave it at that point because I'm going to end up confusing you at this point. All right, so service conductors are always listed as volt amps, not watts. So when we're doing service calculations here, before you know it, you'll see a lot of times we refer to something as VA. VA is the same thing as a watt. And in fact, for the purposes of your exam, it's 100% exactly the same. Now in the real world, that's not true because the volt amps is true power versus apparent power. So you have power factor that comes into play. So there are some loads that are inductive. Inductive loads definitely will change your power factor so you don't have 100% of the same thing. But for the test, they ignore power factor and they ignore other issues. So it is the same for the exam, okay? And remember, P, of course, is just another way of saying the same thing. And then when we're talking about the relationship, remember the top line is division, the bottom two are multiplication. And I like this circle because for me, once I started thinking about it like this, I realized that there's a lot of other calculations that share the same type of relationship. That's a voltage drop. You guys remember your voltage drop formulas?
Yeah.
The V equals, so the way I learned it was probably the way you're thinking of it. V equals 2K I D, all of these are times, divided by circular mils, right? But then there's another formula that tells me how to size a wire, which is circular mils, which is equal to 2K I D over voltage drop. And then if I'm looking for the maximum length, then I have to write it as voltage drop times the circular mils divided by 2 times K times D. And if I'm looking for length, then I got to do it as VD times circular mils divided by 2 times K times I. That's 4 formulas you got to remember if you do it the old school way. Me, I just put it in the same circle because I always know that these two down here are related and these up here are related. And if I'm looking for any one of these variables up here, which I always know what this is, if I'm looking for this one or this one, I'm just going to take the bottom one, whichever one. So for example, if I'm looking for this one, I'm going to take that and divide it into the top. But if you look at the distance or the current, then I just flip it upside down. So it's the same thing, but for me, that visual, that's an easier way to remember. In other words, I put 2Ki up here, D, and then down here at the bottom, I have the two variables, which are going to be voltage drop or circular mils. So what I mean by that is if I'm looking for this formula right here, then if I just erase this number, what I've got left over is this divided by that, right? Make sense? If I'm looking for this, then I'm just doing the exact opposite. I'm doing this formula. And to me, that was an easy way to remember that because it's a visual kind of relationship. And then finally, if I wanted to look for these two, I take that same circle, but I just flip it upside down, and I put the VD on the top, circular mils on the top, and 2K ID on the bottom. And then depending on which one I'm looking for, I just erase that variable. Let's just say I'm looking for that. Well, then that's that formula right there. Right?
K being the constant, right?
K being a constant, yep. Constant based on whether it's aluminum or copper.
Can you say what KID means again?
2 times K, so K is a specific resistivity of a metal, right? And so it's a ratio. The 2 doubles the distance. So the I is amps, like we talked about a minute ago.
And the D is?
Distance, physical distance. Not length of conductor, not length. And you'll see people refer to this as L. That's a terrible thing to call that because it's not length. Length it kind of makes you sound like you're talking about the wire length, right?
You're saying how far the power can go?
Literally the physical separation between the 2 points.
Would that
Oh,
be,
the distance.
The
between
physical,
here,
yep, from here to there and the feet.
Is that what the two is about?
That's what the 2 does.
Right.
The 2 doubles the length for me, so to refer to that as length is confusing.
Yeah.
But if you refer to it as distance, physical separation in feet, then this 2 doubles that number effectively because I've got 1 wire going there and 1 wire coming back, right?
Except for 3-phase.
Except for 3-phase, which is a little bit different
So
formula.
this doesn't apply to three-phase.
It does apply to 3-phase. The only difference is that we use the square root of 3 instead of the 2.
Okay, now, you're saying this could be done in lieu of, the other way, the other form?
Oh yeah. Well, all this is just a way to remember it, right?
Right.
This is the traditional way of doing it, but to me that was always kind of hard